Good morning and welcome to this COSIC seminar. So today for this presentation I will explain you this paper which is called t-SNI Secure Multiplication Gadget for Inner Product Masking. So this is a work that was done by Simon Doge and myself. So let's start with the basics. What are side channel attacks? So side channel attacks are a specific kind of attacks that target cryptographic devices. Basically, the device leaks information. This information can be voltage, can be times, can be temperatures, can be many things, and it depends on the secret data. In this work, we are interested in power analysis attacks. And against these attacks, there exist countermeasures. And the most well-known and used one is masking. So the goal of masking is to make the power consumption independent of the security-sensitive information. So if you have some secret information X, basically what you will do is that you will make a collection of shares. Here in this example, you have D+1 shares, such that, and this is the case of Boolean masking, when you do the XOR of all the shares, you go back to your secret value X. So there exists many different kinds of maskings. You have Boolean masking, but then you have what we call more complex masking types. This can be polynomial masking, inner product masking, and code-based masking. They are more complex in the sense that they use a more complex encoding function, so they have some overhead, just because the mask gadget now is more overhead, is more complex, but they have some benefits. And one of it is that they decrease the information leakage observed in low noise condition. And then you have another benefit, which that they improve the statistical security order. It's an effect that we sometimes call the security order amplification effect. In this work, we were interested in inner product masking. So inner product masking has first a setup phase, where you will define this public vector L. So L is known. It always starts with the 1, and then you use random non-zero value Li. And then to mask a variable X, what you do is that, as always, you generate some randomness, and then for the first share, like X0, basically now you add to the secret value X, not Xi directly, but the multiplication of Li times Xi. And you do that for all the randomness. You get a vector of shares, and then to unmask, basically you do the inner product masking between the vector L and the vector of shares. I mentioned some benefits. So we have this so-called security order amplification effect. And basically, due to the increased algebraic complexity of inner product masking, you allow lower leakages than Boolean masking. Intuitively, with Boolean masking, basically you take 1 bit of the secret, 1 bit of randomness, and you XOR that. But with inner product masking, since you do a multiplication, you start to mix more bit of randomness to each bit of the secret. And what was observed is that the choice of this public vector L, it influences the security impact. And in theory, what you could have is that these order IPM could resist higher order attacks. But there are limitations on the existing mask gadgets in the literature. First, this security order amplification only holds for the encoding. And as soon as you start to perform operation, secure computation on the shares, you lose this amplification effect, especially with nonlinear operations. In order to understand better this security order amplification, we have to introduce yet another masking type, which is direct sum masking, which is a specific case of code-based masking. And with code-based masking, now you work over bits. And now you have a shared vector X and a shared vector of Y. And then basically what you do is that you have some predefined generating matrices, G and H, and you do the multiplication of X times G and Y times H. And basically now you go to code words, C and D, that you sum together. And it was observed that the bit probing security, because now you're on binary level, of this masking type is related to the dual distance of this matrix H. So you can link those two masking types together. And basically now the best bit probing security of IPM can be achieved by selecting L vectors, L values here that can be related to this matrix H such that the dual distance is maximized. In theory, this is what you can obtain. So if you have a 4-bit word, and this is the case with first order or 2 shares, basically you can achieve second order of security, so you gain 1 level of security for free. And if you go up to the best case, in a sense, like this is second order, 3 shares for 8 bits, you can reach up to 7th order of security with only 3 shares. Instead, with Boolean masking, you will have to use 8 shares, right? So this is the benefit that we try to have. And basically, our contribution in this work is that we address the open question of constructing a multiplication gadget for inner product masking that preserve this bit probing security during secure computation. So we preserve this security or amplification. And we showed that the gadget is T-strong non-interfering using the bit probing model. This means that basically we ensure some composability properties on our gadget. And finally, we go to the theory, from theory to practice, and we provide a 2-share 4-bit ARM assembly implementation of our secure multiplication gadget, and we show that it successfully passed first and second bivariate order analysis. Some security definition. I mentioned t-SNI, but first there is the non-interference, so NI, and basically those are composability definition, and you say that a gadget will be t-NI if you have like a total of t probes, and you have 2 subsets of probes, t1 probes that you will place within the gadget, so you can probe intermediate values, and a set t2 of probes that you can place on the output of the gadget. And now you say that your gadget is t-NI if the totality of the probes can be simulated by t shares of each input. If we go to the stronger case now, it's a little bit the same, but now you say the totality of the probes can be only simulated by t1 shares of each input. And this means that the probes that you place on the output shares doesn't propagate back to, doesn't give you more information. This is why you can then have some composability. Then regarding the level of security, we distinguish 2 levels of security. You have the word level of security. This is, as we often know, with word level security when you operate over bytes or word data. This relates to the probing model, so it's related to the number of shares minus 1. And if we go to a finer level, on the binary level, as with code-based masking, for example, now we can evaluate each bit, and now we saw that this is related to the dual distance, minus 1. Okay, let's look at the multiplication gadget that we propose. So the gadget takes 2 inputs, shared inputs, and produces shared output Z, such that if you make the decoding of Z, you get X times Y. This is an example for 2 shared, 2 inputs, obviously. And on a high level, it works in 3 parts. You have a first part that can be like an offline phase where you will generate some randomness. You'll make some randomness and then you place that into matrices Sij that you will use later. In the second part, this is where you do the nonlinear operation of doing xi times yj using the matrix that you made before to remask this result. And in the last part, basically, we just do a compression where we go, in this example, for 4 shared to the 2 shares that we want by just doing a decoding of the tuples here. So regarding the multiplication, the nonlinear operation between 2 shares, so what we want is to ensure, as I said, this bit t-SNI security property, so to maintain the security order amplification effect during secure computation, nonlinear operations. So to do so, we need to be able to operate securely at the binary level. So what we did is that we followed the school book multiplication algorithm to make x0 times y0, which basically you take each bit of x0, you multiply that to each bit of y0, and then you do a squaring. And then you have to take care of the reduction of overflown bits and so on. So to make that, we have a few challenges. To securely mask each binary cross product while preserving the correctness and the word level t-SNI security after recomposition in the field. And then we have to take care as well of the reduction. On a high level, this is how we do the nonlinear operation. So we start with two shares, xi and yj. Those are now represented as vector, so those are k size vector, because we're in the field 2 power k. And basically, in the first step, we do this tensor product or this schoolbook multiplication of xi times yj. Basically, we end up with the matrix C tilde, such that if you do the XOR of all of these rows, here now you will go back to a vector that will contain each bit of xi times yj. But we have this matrix, now we refresh this matrix using the pre-made randomness matrix Sij. We'll see later how this is constructed, but basically the matrix Sij is using a collection of what I call IPM0, which is the generator of randomness value 0 using inner product masking. So basically you will use some bits of a masking of a value 0. So you remask this C tilde matrix, you end up having your matrix of the output. You do the compression where you go from the matrix representation into a vector, so you XOR each of the rows, and basically then you go from this vector representation f to k to f to power k, and you get your first output, which basically is the remask xi times yj. Let's make a full example. So you have a two shared x0, x1, y0, y1. We assume here a 3-bit field. And I will explain you how we made this randomness matrix. So to make those 4 matrices, basically we have to generate 12 two-shared IPM of 0. So those are sharings of 0, as I mentioned before. So we have S0 to S11. Each of those Si are basically a two-share encoding of 0. And we have the same 6 two-share IPM0 from R0 and R5. Each of those are as well just a two-share masking of a value 0, right? And now we specifically combine those values. So basically we take the first half of those Si, so from S0 to S5, and then we take the first shares of those and the first shares of the Ris. And we add that together, we have the first elements of our matrix. For the second matrix, basically, we now just take the second shares of this first half. So basically, these elements Si from 0 to 5 and 0 to 5 here are the corresponding two shares of each of those masking of 0. And similarly, we do the same for the second half. Now, when we have these done in an offline phase, we can go to the online phase where we make this whole multiplication. As I mentioned, we follow the schoolbook multiplication. We have this C tilde matrix here. This is just the matrix such that if you do the XOR, you go to x0 times y0. And we have to pick our S00. We represent these as a matrix. And then basically we just do the XOR. And at the end, what you obtain is you perform the XOR of every row, and you map that to the field representation. You end up to having this x0, y0 plus a collection of first shares and a collection of first shares here. If you do that for all the xi, yj, you end up having this result in the part 2. And because we took the specifically made random matrices, basically when we do the compression part, those elements here, they decode to 0 because we do a decoding here. We unmask. These are the first share, the second share, similarly for here, and we end up having some randomness here that will decode correctly. Quickly regarding security, every row is independent. If you take every tuple or pair of rows, just because you're using shares or bit of shares of distinguished sharings. Similarly, for every columns, every set of T1 column is independent because we're using generators IPM0, which we prove to be t-SNI as well. Some words on the algorithm efficiency. This is only on the online phase, so basically here, what we want to compare is the number of gates on the y-axis and some bit security order. So we check at the number of AND gates and XOR gate. We compare our multiplication gadget with Boolean masking using some ISW multiplication algorithm. You have the 4-bit case and the 8-bit case. And what I want to say here is basically thanks to the inner product or the security order amplification of inner product masking, basically at some point you can maintain smaller number of shares for a good level of security, and then you start to use less number of gates compared to Boolean masking that needs to increase all the time the number of shares. And this is what we see for 5th security order, we start to use less number of gates. I mentioned this IPM0. So you saw that our algorithm relies on the generation of those inner product masking of 0 to refresh the shared values. We use this quite a lot, but basically these gadgets needs to be as well t-SNI bit probing secure. And to make a generator for this randomness, basically we use the work by Ishai et al. And we generate that by making t+1 regular encoding of 0 using IPN, and we XOR them together. And then with that, we can be assured that this is the other bit probing secure. You don't really need to have a t-SNI. In practice, you can use t-1, but what this means is that now the randomness cost is not free. With Boolean masking, you can just pick the randomness generated and use it directly. Now, because we operate on the randomness before we use it, we have to take into account this cost. And this is an overhead. This is quite a bit annoying for this algorithm. It's some kind of bottleneck. So because now, to make one of those secure gadgets, you have to make t times this cost. And this is an impact. This is the randomness cost just of our multiplication gadget. You have the 4-bit case, the 8-bit case in dashed line. And you can see that basically just the numbers blows up quickly. Because now you have a high cost of randomness generation. And this is, I mentioned, the bottleneck. But we believe that we can optimize that. And we left that as future work. In terms of practical efficiency, now we compared the cycle counts of the online phase of a multiplication gadget, and we compare with ISW. You have the regular one and the one that uses the log-a-log multiplication optimization. And this follows somewhat the algorithm efficiency that we had before, that at some level of security, then you start to use less number of cycle counts compared even to log-a-log. But obviously, if you take into account this pre-processing of the randomness, if you take that into an online phase, then it has some large added numbers. Regarding now, we went from theory to practice, and we test that. This is the 4-bit evaluation. So on the upper left, you have the first order evaluation. This was expected not to leak, obviously. We test, you have the usual red line, which is a plus minus 4.5 threshold. This is for TVLA. And then basically we did the bivariate evaluation. So now we have to pre-process the trace, and we took the center product for each of the tuple points that you can have. And we evaluated different parameters for this public vector L. We went from weakest to strongest. Basically, we started with the L11 values that you see just here. This is basically Boolean masking. We know it will leak, and it does. You have this red dots here and there, meaning leakages. And then we tested some parameters, which now we know from theory is not second order secure, but we'll start to mix more bits of randomness. So we expected that to leak, but less, and this is what we observe here. And finally, we use the correct parameters that we know from theory will assume second order security. And we see that for 1 million traces, we don't have any leakage detected. This is just the max peak evolution that you will have with increasing number of traces. You can see that with wrong parameters, it quickly blows up and goes above the threshold, but with the correct values, then stays something that stays flat up to 1 million traces. So in conclusion, we did detail a t-SNI secure multiplication gadget that was tailored for inner product masking. This enables to preserve this security or amplification during computation. So we can exhibit lower number of gates than the standard ISW in the online phase, but obviously we have some overhead due to pre-processing phase that compared to Boolean masking. And finally, we performed the practical side channel leakage evaluation on an ARM assembly implementation, and we didn't see any leakage for 1 million measurements. Some future work to conclude. So you saw the limitation was this randomness. We can try to reduce the randomness, try to optimize the randomness cost to generate this IPM0, and as well the number of instances that we have to make. We can try to optimize the implementation, might benefit from bit-slice or vectorized techniques. And finally, we would like to extend that to code-based masking. This was tailored to inner product masking, but in its current state, it is incompatible with code-based masking. And having the same properties maintained for code-based masking would be nice, because code-based masking enables you to use more flexible matrices compared to inner product masking, where you have to use some field element Li. Now with code-based, you can have more freedom, and this enables you to maximize this dual distance, or this security order amplification. This is the end. Thank you. If you have any questions. Yeah. Yeah, you're right. You're right. Basically, this is something we often do when we do some TVLA. We then do a test without the randomness. So you don't use the randomness. Basically, it's just to show that it will leak, because you don't use randomness, but it leaks quickly. And yeah, it's often a not very interesting graph, but you're right. Yeah, yeah. 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 More than this, you mean? It will probably, if you extend that to code base, so if you have a general algorithm, that might need the same situation. If you follow this procedure of using encoding of 0, so now you will have code base encoding of 0, which will have the same limitation, I would say. Yeah, I will say same. No more instances, at least. But then you could optimize by making a specific implementation. How we can optimize the randomness cost? So we saw from the proof, the pen and paper proof that we did, that there are some cases where you cannot, the simulation don't need anything, like you don't need that many randomness. So at some point you could remove a bit of randomness and it will not impact the security. So this will be one approach. And then a second approach, it's not clear. I don't know yet. We'll say, so we used this approach of using encoding of 0, because we said that if we use as element for refreshing a generator that is t-bit SNI, then you know you can maintain the security. If you go directly with Boolean masking, with randomness directly, then you could have some similar approach, maybe, if you have enough randomness, but then maybe the proof might be more difficult. It was a trade-off to try to have a framework where the proof is not too hard to make. And all right, thank you.